One thing I'd like to add to what I said earlier is that this is the definition of a Bronsted-Lowry acid and the definition of a Bronsted-Lowry base. There is the Arrhenius definition, there's a Lewis definition. For the purpose of this course, if you concentrate just on this particular one, acid donates a proton, base accepts a proton, that is sufficient. And if anybody asks you about an acid or base, well, tell them that you just go according to the Bronsted-Lowry definitions for donating and accepting a proton. Okay? So, acids, molecules are both organic and inorganic. Cations contain a hydrogen ion, anions that contain a hydrogen ion. Bases are ionic compounds that contain a hydroxide ion. Molecules, primarily amines, so that ammonium, for example, is NH3. Ammonia is NH3, but as a base, it accepts a proton to form NH4, right? Anions with and without H, and cations, there's a few examples of those as well. So when you have anything that forms an acid, a species that's formed when a proton is removed from an acid is the conjugate base. So if you have HCl, the conjugate base of that would be Cl, wouldn't it? Likewise, a species formed when a proton is added to a base is the conjugate acid of that base. Okay? So that NH3, when a proton is added, is NH4 plus, that would be a conjugate acid of the base NH3. Okay? So when a proton is removed from an acid, it forms the conjugate base of that acid. When a proton is added to a base, it's the conjugate acid of that base. A species that can accept or donate a proton is called amphiprotic. Key one there is water. In the presence of an acid, water acts as a base. In the presence of a base, water acts like an acid. Here you have water. Here you have OH, presence of a base, right? So, this is the conjugate base of this. Here you have NH3. This is the conjugate acid where you have added the hydrogen. Okay? So this is the acid in this case. This is the base in this case. This forms the conjugate base and the conjugate acid. Acids and bases are on one side. The conjugates are on the other side. Okay? Properties of acids, they have a sour taste, but don't go tasting them. Just take my word for it. Okay? Maybe if you have a very dilute one, for vinegar, for example. I guess some people do take vinegar at a lower concentration. And it also is changes the color of certain materials. It will turn litmus paper red. It reacts with active metals, magnesium, zinc, to release hydrogen. And it neutralizes bases formed in water and salts. Those are the properties of an acid. Properties of bases, they have a bitter taste. Okay? Reverses color change. In other words, this will cause red litmus paper to turn blue. It's slippery on the skin, and because the caustic acid action of it is converting tissue into a soluble material. Okay? So it's best not to put a base on your skin. But when you work with the cleaning solutions, your skin will feel slippery afterwards, and that's because you're losing tissue there. And also, bases will neutralize acids, forming water and salts. Typical ones are sodium hydroxide, potassium hydroxide, ammonia, calcium hydroxide, magnesium hydroxide. And these have common names. You have all of these in your kitchen. Sodium hydroxide is lye, caustic, used in oven cleaners and drain cleaners, right? Oops. Potassium hydroxide is potash. It's used in a very strong one, used in drain cleaners. This is also used for stump removal. Weak base, used in household cleaners. That's your window cleaning solution. This is called slaked lime. It's used to make brick and mortar. This is called milk of magnesia or antacid or a laxative, right? So, acid is a proton donor when dissolved in water. Base is a proton acceptor when dissolved in water, as I mentioned earlier. And this is exactly the way in which those reactions take place. Okay? Here the hydrogen is going to there. Here the hydrogen is going to there. Strong acids, these ionize completely in water. Nitric, sulfuric, hydrochloric acid. Strong bases completely ionic in water. Sodium hydroxide, calcium hydroxide, those are the different examples there. Weak acids, these are partially ionized. One example is acetic acid, which is vinegar. Weak bases are partially ionized. This would be ammonia, magnesium hydroxide, ones like that. Just giving you some. Pepsi and Coke have quite a bit of acid in them. That's phosphoric acid, by the way. Lemon juice, this is acetic acid as well. This is wine vinegar. This is also acetic acid. And you have acetic acid in these as well. You may have some acetic acid, but it's primarily phosphoric acid is what helps clean the bugs off your windshield from using a Coke or Pepsi solution. So in pure water acts as both an acid and a base. And this right here gives you the concept of Kw, okay, the equilibrium constant of water. So you have is equals 1.0 times 10 to the minus 14th, okay? So that means that the concentration of the hydrogen ion and the hydroxide ion is each going to be half of that. It's going to be 10 to the minus 7th, right? And that's an important thing to remember. So in pure water, this concentration times this concentration, and this should be x squared equals x squared equals this right here, right? This should be x squared because you have one concentration here, one concentration here. So these two are equal, okay? This is 1 times 10 to the minus 7th. The square root of this number right here is 1 times 10 to the minus 7th. Okay? So whatever one is, the other one is. And so in pure water, x squared equals 1.0 times 10 to the minus 14th. So in any acid or base solution, you've got additional ones where this is not equal to this. Okay? It's going to be true that these two combined will still equal this, so they're inversely related to them. If this ion is greater than 1 times 10 to the minus 7th, then this right here has to be less than that, doesn't it? And the solution is acidic. If this is greater than 1 times 10 to the minus 7th, then this is less than that, and the solution is called basic. Okay? So the acidity and basicity can be expressed in terms of the concentration of these ions or of these ions. These concentrations can span many orders of magnitude, right? We went from 10 to the minus 14th to minus 10 to the minus 7th, 10 to the minus 1st. And so what we do is we use a term called pH. pH is the log of this hydronium ion concentration. It's actually the minus log of the hydronium, minus the log of this thing right here. But don't let that bother you too much. So, if these are both the same, then this right here is the concentration is 1 times 10 to the minus 7th, right? Then the solution is considered neutral. pH equals POH equals 7.0. Why I said it's the minus the log is because this right here, the log of this right here is going to be minus 7, isn't it? This is going to be minus 7 as a log. And so instead of having minus 7 here, this right here should be, that's why it should be the minus the log of that number. So if this right here, oops, sorry about that. So pH less than 7 and POH greater than 7 means the solution is acidic. If a pH is greater than 7 or the pOH is less than 7, you have something that is basic. Water is weak. We use 10 to the 10 notation, powers of the 10 notation. Strong acid, this is increasing. Here are some examples of hydronium ions. Okay, so the pH, low numbers here. Okay, and these are to the minus numbers. This is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. Okay, this is 10. This is the reciprocal of it. Okay, so yeah, these are to the minus numbers right here. So these are the moles per liter, and so that gives us this pH right here. So this is increasing acidity this way. This is decreasing acidity this way. Okay. So hydrochloric acid, your stomach that's 0, 4% of that. 1.6 to 1.8. Lemon juice, vinegar, carbonated soft drinks, grapefruit. That's why if you drink too many of those carbonated soft drinks, you can have acid problems in your stomach. Acid rain, tomatoes. Tomatoes are fairly neutral. Potatoes, natural rainwater, then milk. Then you get to those seawater, blood, 7.4. Blood is actually a buffered solution. It's in a range right here. Bicarbonate solution, that also is a buffered, and so that has a range. And you have the sodium hydroxide is a very high base material. So the Bronsted-Lowry are hydrogen ion donors, as we mentioned. Strong acids are 100% hydronium ion. Weak acids are much less than that. The relative strength of weak acids can be determined by measuring their equilibrium constant. So you have this sort of an equation right here with an equilibrium constant Ka. This is the acid ionization constant. And so the Ka value is just going to be the concentration of this times the concentration of this divided by the concentration of this. Again, this is a liquid. This has a value of 1 for this one. So Kas are related to the strength of the acid. The larger the Ka of an acid, okay, the stronger the acid is. And the smaller the Ka of an acid, the weaker the acid is. So likewise, bases work the same way. You can have the same type of an equation where you have a base dissolved in the water giving you this ion and this ion. Strong bases are nearly 100% ionized. Weak bases much less than 100%. The relative strengths of weak bases can be determined by measuring their equilibrium constants. This is the base ionization constant, K sub B. Okay? All we're doing is just denoting the differences between B, and then remember for the acid, it was a acid ionization constant for Ka, and for the solubility for how much is precipitating, we had K sub Sp, right? So it's the same form. The concentration of these two, each one individually, raised to the power of any coefficient in front of them in the numerator. Anything over here to that concentration in the denominator. Okay? And these are related. The larger the Kb value, the stronger the base, the smaller, the weaker the base. So, again, Ka of this times K sub B of the conjugate is going to equal 1 times 10 to the minus 14th. So, what this just points out is that Ka and Kb are inversely related, just as we saw the pOH and the pH, or the values, are inversely related. So the extent to which an acid donates a proton in water depends upon the strength of the conjugate base A+. This is the conjugate base, right? This is the acid. Okay, this is the acid right here. This is the conjugate base of this acid. If this is a strong